Okay, let's look at a little exercise involving rotational kinetic energy, which is what this question is asking here. So let's first start with extracting what's given to us. So we have given information, important information. We have a diameter of 0.2 meters, right? That's important. So we have diameter equals 0.2 meters. The mass is equal to 3 kilograms. And it's rotating at 2200 revolutions per minute. So omega is equal to 2200 RPMs. And there's another very important thing that, well, two other very important pieces of information here. One, when we're looking at rotational kinetic energy, we don't need just the mass of it, but we also need to know the shape of it, how that mass is distributed, and the axis that it's rotating around, right? So we need to know that it's a shape of a solid disk and it's rotating about an axis through its center. So we have, here's the disk like this, here's the axis it rotates around, and it's rotating like this at 2200 RPMs. This is because when we look at your rotational kinetic energy, Ke rotational, this is 1/2 I omega squared, right? Versus linear kinetic energy, we just had 1/2 mass times the speed squared. But this I, this rotational inertia, remember mass is actually the way we quantify the linear inertia, but I is rotational inertia, and this has to do with how the mass is distributed about the axis it rotates around. So you need to know the shape of the object as well as the axis it's rotating around. These are really important things that we didn't have to know, and also the mass of it as well we need for I. Previously with linear inertia, we just needed the mass of it, but rotational inertia is a little bit different. So really important thing, the fact that it's a solid disk is also very important. Solid disk and rotating about an axis to its center, which I've drawn here. Okay, and what we're asked to find is, so important thing, when we're extracting information with something rotating, make sure to pay attention to the shape and the axis it rotates around. That's the takeaway there. What we're being asked to find is the kinetic energy, right? It actually asks us just for the total kinetic energy, right? So it asks us what is its kinetic energy. Well, it only tells us it's rotating, it's not translating, so we really only have rotational kinetic energy, right? So this is Ke rotational. Okay, and then the solution, and that's for part A, and then for part B would be how high to have the same potential energy, right? So H for same gravitational potential. So the solution, we have rotational kinetic energy is equal to 1/2 I omega squared. Now you have to remember too, when we derive this formulation for rotational kinetic energy, it relied very heavily on the fact that omega was in radians per second. So we have to have this in radians per second or we can't use this equation. So basically, if you're unsure, convert omega to radians per second. There are times when we don't have to, but if you're ever unsure, just convert this to radians per second as your kind of go-to. Okay, so first we should do that. Let's say we have omega is equal to 2200 revolutions per minute times 2 pi radians per revolution times 1 minute per 60 seconds. And so omega is equal to 230 radians per second. Okay, there's a 2 pi. And then we have to look this up, a table. We look it up in our table for rotational inertias. So I is equal to, this is for a solid disk, and this is equal to 1/2 mr squared, where r, this is the outer radius, and so this is equal to, this comes from a table of rotational inertias. Like I give you on the equation sheet for the exam 3 equation sheet has a table of rotational inertias. It's also in your textbook, but you can just use the one that I'm going to give you on the quizzes and exams. Okay, and this mass is the total mass, right? This is the total mass here. And so just writing this out then with the kinetic energy, then this is 1/2 I omega squared. Let me write this out as 1/2 times 1/2 mr squared omega squared. And then I have all these things, right? We have omega in radians per second. We have the radius we were given to us, or gave us the diameter, so the radius is half that. And then we have the total mass, right? So we can get our rotational kinetic energy. Maybe I should have put a rotational here. And so this becomes 1/4, right? 1/4 times the total mass was 3 kilograms, times the radius is 0.1 meters squared, times 230 radians per second squared, and this rotational kinetic energy is equal to 397 joules. And there we have part A. Okay, so just like linear kinetic energy, but we have to do two things. We have to make sure that omega is in radians per second, and we have to find our rotational inertia as opposed to just the mass. And then part B is sort of just a review of potential energy. They want it so that our kinetic energy is equal to the gravitational potential energy, which is equal to mgh. And so we just say here that the height this would have to drop from is the kinetic energy divided by mg. So this is 397 divided by 3 times 9.8, and that comes out to 13.5 meters is the equivalent height. So if I had, this is part B, if I had 3 kilograms of this material and I dropped it 13.5 meters, it'd be the same amount of energy as this thing in this shape, this spinning. And actually there's some ways, with renewable energies, one of the difficult things with renewable energies is finding a way to store that energy, because it's not necessarily produced when it's needed. And one of the ways that it's actually stored sometimes is making a bunch of big wheels. They call them flywheels, and they just spin them very quickly, and then that can store, and they put it on very, very low friction bearings, and then they just have them spinning, and there's just a whole bunch of them spinning, and you can turn, take the energy off it whenever you need to. So I guess if I had 3 kilograms of water fall this far, if I could take all that energy and store it, and I had a disk that was the configuration up here, then I would need to spin it at 2200 revolutions per minute to store all that energy from that 3 kilograms of water from the waterfall.